Astronomical students, in the previous lecture we discussed how to derive the coefficients of multiple linear regression model in two independent variable case. In this lecture we will discuss how to derive and how to interpret the coefficient of multiple determination in multiple linear regression model. We have discussed in the simple linear regression model that R square, the coefficient of determination, shows the percentage of variation in y that is explained by our x variables. In simple linear regression, there is only one independent variable, but in multiple linear regression, we have more than one independent variable. So the interpretation of R square would change a little bit, not much, only a little bit. So in multiple linear regression, the coefficient of determination is known as coefficient of multiple determination. In simple linear regression, it is simply the coefficient of determination, but both tells us the same thing. Both tells us how much variation in y is explained by our x variable. So there is no difference between the coefficient of determination and coefficient of multiple determination. Only the distinction is simple regression or multiple regression. So now here we can define the multiple r square or simply the r square. The coefficient of multiple determination tells us the percentage of total variation of y that is explained by our included x variables. Together, it means that how much variation in y is explained by our x variables jointly. For example, if the coefficient of multiple determination r square equals 0.9 and our model is consumption function where the independent variables are the price level, the interest rate and the disposable income. So the R square can be interpreted as 90% variation in consumption is explained by disposable income, interest rate and the price level in the economy. So the interpretation is same. So let's derive the coefficients, derive the coefficient of multiple determination r square in multiple regression. So remember that this is our sample regression function in two independent variable case where y equals beta naught plus beta 1 x1 beta 1 hat x1 plus beta 2 hat x2 plus u hat, where this term equals to y hat. So y hat equals beta naught hat plus beta 1 hat x1 plus beta 2 hat x2. We can derive this sample regression function in the deviation form. So remember that the deviation forms of variables are represented by the small alphabets. So here small y is the deviated form of our dependent variable and small x1 small x2 are the deviated forms of our two of the independent variables. So this is our sample regression function in deviation form, which is same. You can see that this is the same, only the difference is that it is the SRF of the actual data and this is the SRF of the deviation form. So you can here see that in the deviation form there is no intercept. I have proved it earlier in the previous lectures. So this term again equals to small y hat. So we can write small y equals small y hat plus small u hat. So these all are the deviated forms. Next, sum and square. We have sum and squared this equation, and we get this equation. Sum of y square equals sum of some y hat squared plus sum of u hat squared. So remember, from now these y's and these u's and this x are in the derivation form always. So the sum of u hat square can be written as sum of u hat, which can also be written as sum of u hat into y minus y hat, because u hat equals y minus y hat. So this can also be written as sum of u hat into y minus, I have substituted the value of y hat here. So this is our y hat. You can see that this is our y hat. This is our y hat. So when now you need to open this bracket, we get this equation, and then I have multiplied all these terms with this term. I get the answer in this form. Now remember that the covariance between u hat and x is 0. Therefore the sum of u hat times x1 sum of u hat times x2 equals 0. We have proved that in the numerical properties of sample regression function, that the covariance between x and u hat is equal to 0. That's why this term and this term is 0. The covariance between x1 variable and u hat is 0, and the covariance between x2 variable and u hat equals 0. So this whole terms becomes 0. So what is left? That this sum of u hat square equals sum of u hat times y. And remember that the sum of y times u hat, this is our u hat. This is our u hat. U hat equals y minus y hat. So now I have substituted. So now I have multiplied this these terms with this term. So I get this equation. Now you can see that this is the equation for sum of u hat squared. This is our sum of u hat square. Now substitute sum of u hat square in equation 1. What is our equation 1? This is our equation 1. This is our equation 1. So I have substituted the value of sum of u hat squared. So sum of u hat square equals this term. So sum of y square equals sum of y hat squared, this one, plus this term, which comes from this equation. So here you can see that if I move the sum of y square to the left hand side of equation of equal sign, then the sign becomes negative, and they both cancel out. And then when I solve this equation for sum of y hat squared, I get this equation. So sum of y hat squared equals beta 1 hat sum of x1y plus beta 2 hat sum of x2y. Now remember that sum of y hat squared is our explained sum of square, and the formula for r square equals explained sum of square divided by total sum of square. So this is our explained sum of square divided by total sum of square, which is sum of y squared. So the r square formula in multiple linear regression for the 2x variable case is r square equals beta 1 hat sum of small x1 y plus beta 2 hat sum of x2 y divided by sum of y square. Remember that all these variables x and y variables are in the deviated form. So you first need to convert the x and y variables into the deviation form, then we can find this r square formula. Note that When you find the coefficients of multiple linear regression, it becomes relatively easy to find the R square, because this term and this term and beta 2 hat and beta 1 hat, you have already found them. Where? Here you can see these are the formulas for our coefficients in the multiple linear regression for two independent variable case. Look at this formula. You have already found sum of x1 y, and you have already found sum of x2 y. You have already found the beta 1 hat. So these are the requirements for this formula. So when you find these formulas, you can find automatically the R square, because all the things you have already found. And what is this sum of small y square? It is the sum of y minus y bar squared. Now look at this. This is the R square formula for three independent variable case. If there are three independent variables, then R square formula would be look like this, where R square equals beta 1 hat sum of x1 y plus beta 2 hat sum of x2 y plus beta 3 hat sum of x3 y divided by sum of y squared. Compare this formula with this formula. What is the difference between two formulas? You can see that in this formula only this term has been added. Beta 3 had sum of x2 y. This term has been added because there are three independent variables, so I have added this term. And now look at this formula here. The beta 3 had sum of x3 y is not found, because it is the formula of R square for two independent variable case. Only the difference is in the nominator. Denominators are the same. So if you increase one variable, you need to add uh, another term. If for example you have a k variable case, then the nominator would be like beta 1 had sum of x1 y plus beta 2 had sum of x2 y up to beta k had sum of x k y divided by sum of y squared, which is the same. So remember that when you increase the number of independent variables, the nominator will increase. If the nominator increase, then R square will always increase, because if a nominator increases but denominator remains the same, then the overall ratio increases. So that's why R square will always increase here. So remember that you can see that as you increase the number of independent variables, the nominator of R square formula increases, while the denominator remains the same, because we are increasing our independent variable while the dependent variable is same, only one dependent variable. That's why the denominator will not change, only the nominator value will change as we increase the number of x variables. So while the denominator remains the same, it means that as you increase x variables, the R square will always increase, even though the additional x variable is less important in explaining why. It means that even if the xk variable is less important, but the R square will always increase. So this is the property of R square, that R square is the non-negative function of additional x variables. It means that as you add more and more x variables, the numerator becomes larger while denominator becomes remains same. So that's why R square will always increase. even though the additional variable is less important. So this is an important property of R square, and this is also the drawback of R square. Because if the additional x is not important, then why R square should increase? So this is the issue that we will discuss in our coming videos.